Right, this is actually a step 3 question from 2011 question number 8. It's question 3 from the step 2 complex numbers support booklet because this kind of topic here was changed in recent years to be from step 3 into step 2. So if you're preparing for step 2, you might need to expect to see stuff like this. So okay, we have W equals this in terms of Z, W and Z being complex numbers themselves, Z being this one, W being this one, and it wants us to give U and V in terms of X and Y. So, okay, well, we're obviously going to have to throw X and Y's into here. So replace Z with X plus IY and replace the omega, or the W, I think that actually is, with a U plus IV. And okay, how are we going to express U in terms of X and Y and V in terms of X and Y? Well, what we're going to do is we're going to take this complex number, which is what it is, and we're going to write it in the form A plus BI, because then we could just compare the real parts and compare the imaginary parts, and we'll end up with U equals something in terms of X and Y, and V equals something in terms of X plus Y. So that's the idea. How do we do it? Well, of course, right now it's got a messed up denominator. So if we just do some work and get it in terms of a nice complex number in the form A plus BI, we can then realize this by timesing it by X minus I into 1 plus Y, right? Because the cross terms will go away, the I squared will become a minus 1, and it will all be a nice real denominator in terms of X and Y, which is exactly what I want. Need to times the top by that, of course, as well, because otherwise it's just not going to be a thing that I can do. This is really annoying. There's a bunch of multiplying to do, but eventually it ends up okay. Notice how I'm doing as little multiplying as possible because I'm just kind of hoping stuff will cancel immediately, and it does, which is nice. So this cancels with this, which gives us our nice real denominator. More things cancel on the top once you spot them all. More things cancel, cancel, cancel. You end up with this. And of course, this is fantastic because I can split this in half here to leave me with this thing over the denominator plus I lots of this thing over the denominator. And then I'll just compare U's and V's, and I'll get U is equal to this business, and V is equal to this bad boy right there. And we'll be done with the first part of the question. We'll leave those there because they'll be very helpful. By setting x equals tan theta over 2, I'm quite happy to see this because I do lots of this in integration sometimes when I get desperate enough to use t formulas. So quite used to this substitution. So hopefully we're onto a good thing here. And also y is 0. I'm even happier to see because if y is 0, that just makes these two things 2x over x squared plus 1 squared, which is 1, and x squared minus 1 over x squared plus 1 squared, which is just 1. So okay, I can work with these two things as well. That looks good. So let's put the tan theta over 2 into here. So putting it into the use first, we get this. Tan squared plus 1 is sec squared, which is fantastic. Sec squared dividing by sec squared is the same as timesing by cos squared. And of course, because tan is sine over cos, one of the coses will cancel, and you'll just be left with sine cos on top. And this should hopefully look fairly recognizable because it's 2 sine cos. Where do we know 2 sine cos from? Well, I think we know that sine of 2 theta is 2 sine cos. And of course, this is the double angle formula. We can double this angle to get to this one. So of course, if this was theta over 2, it would just be just as valid, doubles to get sine of theta. And so therefore, this is sine of theta. Fantastic. U is sine of theta. Let's do V as well. So just throw in the substitution into the V one as well. And this again is sec squared, which is timesing by cos squared. Tan squared is sine squared over cos squared. The cos squareds will cancel. So this will just be a sine squared. And then, of course, minus a cos squared. This should also look recognizable because it's the double angle formula for cos. If we halve all the angles, we get this. And, of course, if you times it all by minus 1, you flip them over. And you end up with this as minus cos theta. So we have V equals minus cos theta. And yeah, this seems like it's a locus that we can sketch. It doesn't actually ask us to sketch it, but I don't care. We can sketch it anyway. We get, of course, that sine squared plus minus cos or squared is of course equal to 1. I should have maybe written these the other way around because that of course this leads us to this or whatever, it's fine. Yeah, u squared plus v squared is 1 from here because of this line, so fine. Now, where's this 1 point emitting business? By the way, so this is of course a circle centered at the origin radius 1 in the UV world. But where's this point emitted come from? Well, if theta were pi, then we'd get x as tan pi over 2, which is undefined. And so therefore, if theta is pi, we can't actually sketch this at that point. When theta is pi, we get sine of pi is what, 0? So u is therefore 0, and cos of pi is minus 1. Minus 1 is plus 1. So we emit the point u is 0, v is 1. So okay, we take a circle radius 1 centered at the origin, and we emit the point 0, 1. So it will look a bit like that if you want to sketch it, I guess. Question 2, or part 2, this time y is 0, which is the same as what we had before. So we can use these results still. But x is bound between minus 1 and 1 this time, specifically. So we still have all the same business. But this time, if x is bound between those two things and can't just be anything, then let's think about the restrictions therefore on theta. Now, on the previous question, if x was just between minus infinity and infinity, that means you could make theta anything between minus pi and pi, because that would get you between tan of pi over 2 and tan of minus pi over 2, which is, or that's a function that goes from negative infinity all the way to positive infinity, so you get all the values of x out of it, which is why there were no more restrictions other than the one that we found. However, if x is limited in here, that means theta is also going to be limited. So, okay, well, let's arctan of 1 and arctan of minus 1 to get, of course, these two things here, and then double everything, and we end up with theta has got to be between these two things only. So then we go into here and we think, okay, well, sine theta between minus pi over 2 and pi over t, well, that actually just goes from minus 1 up to plus 1. So u is therefore between minus 1 and plus 1, which is actually exactly what it was before with a circle radius 1. Of course, it's trapped between minus 1 and 1. However, v, because cos is an even function and looks the same either side, between minus pi over 2 and pi over 2, that goes from 0 up to 1 at x equals 0 or theta equals 0, down to 0 again. So it just does a loop like this between those two values. And so it's trapped between 0 and 1. Except because it's minus cos theta, it's trapped between minus 1 and 0. Just flip it over. So therefore, it's the same as the sketch we did before, except for v, which is the y-axis in this case, v can't be positive. So it's just got to be down here, and that'll be the sketch. No points omitted, because the point that was omitted was up there, and that no longer exists anyway, so that's fine. Now we're going to do a very similar thing, but this time x equals 0. So okay, let's put x equals 0 into here. And this reminds me a lot of, well, it's similar to lots of step questions in that it's similar to what we just did, except we're going to have to do something a bit different, right? So if x equals 0, u equals 0, obviously, because it's 0 of something, and v equals this. So now let's draw the locus of this. Now, of course, we can spot a difference of 2 squares there, which is very nice, and we'll end up with this. And now we need to think, okay, well, what does that look like? What's the locus of this? U is 0. If we're thinking about the UV axis, U is 0 means we're trapped on the V axis. So are we just anywhere on the V axis? But now look at this here. And again, Y, also important. Y is trapped between minus 1 and 1. What I decided to do here was add 1 to the top of this fraction just to take it away. And then I can break this here to say it's 1 minus 2 over this. It's a very common trick you see when you're trying to identify ranges of things. Because now I can see, well, okay, the function is never bigger than 1, right? I don't think. Certainly it's never big. Well, so let's put in the smallest thing. If y is minus 1, which I know it technically can't be, it's 1 minus 2 over 0, which is, so it's 1 minus infinity, essentially, sort of, which is sort of minus infinity. So this function, this v, definitely goes as far down as you want it to. If y is 1, we get 1 minus 2 over 2, which is 1 minus 1, which is 0. And if you're less than that, we can sort of quickly work out, like if we try y as 0.9, it's 1 minus something slightly smaller than 1. So therefore it's going to be, sorry, 1 minus something slightly bigger than 1, because it's going to be like, if y is 0.9, it's 2 over 1.9, which is something slightly bigger than 1. So 1 minus that is something negative. So this ranges from up to 0 when y was 1, down to negative infinity. So it's trapped on the v-axis, as we said before. But it's only the negative part of it, only the negative part of it. And I think, and it doesn't go through the origin, maybe my picture. And in fact, it didn't ask you for a picture, so maybe just say that in words. But it's the negative part of the v-axis. I think that's what we have to say in words, and we're good to go. And now, last part, again, similar in the sense that it's this. If you compare part 4 to part 1, was it? Yeah, compare part 4 to part 1. It's basically the same, except y is now 1 instead of 0, with x having the same thing. So look at this question, basically the same as this question, except they haven't given us this hint, mostly because I don't think this would work, but it's very similar. So let's do some similar things. Let's put y as 1 into here to work out u is this and v is this. Of course, 1 plus 1 is 2, squared is 4. That's where that comes from. And now, okay, well, let's think about this. The previous time, we used the substitution x equals tan theta over 2. Because previously we had x squared plus 1 on the denominator, which of course becomes a sec squared if you put in tan. Now we've got an x squared plus 4. So the trick will be use x equals 2 tan theta over 2. Because when we square that, we're going to get 4 tan squared theta over 2. We'll be able to factorize out the 4 and that will leave behind a tan squared theta plus 1. So I reckon this is a good shout. If it doesn't work, step questions, you have plenty of time, try something else. But this seems like the most promising candidate solution because it's very similar to what we did before, which is what step always likes you to do, but also different enough to have hope of doing the same sort of thing. And that's the key that we're looking for in step questions. So, okay, we square both and we end up with this. As I said, 2 lots of this is just this. This, I mean, all the 4s cancel immediately. Tan squared plus 1 is sec squared. Tan is, which is, of course, timesing by cos squared. So you get sine over cos, which is tan, times cos squared, just becomes, I think, sine cos. So I know I did that very quickly, but it's the same as what we were looking at before, right? So I'm just going to say it all out loud. Of course, we've seen this before as well. This, I think, is a half sine theta, based on the fact that sine theta is 2 lots of this. So therefore, just halve it. Okay, and the v, put it in the v as well. Very similar. I mean, you can actually just go from here, right? This is the same thing as before, except you've got an extra tan on top. So in other words, you've got an extra sine over cos. So if we take this and have an extra sine over cos, the coses cancel, and you just end up with sine squared theta over 2. Well, okay, I'm not too happy about trying to draw this from here. Not that I have to draw it, I don't think. I just think I have to just say what it looks like. But I'm still not happy about that, mostly because it's a sine squared, but also theta to theta over 2 never makes us happy. We always want to have the same arguments. So let's turn this into a theta argument. Of course, we can do that by using the cos double formula, rearranged for just in terms of sine squared, and we'll end up with something like this. We can replace a with theta over 2 to make that a cos theta. So it's a half minus a half cos theta. And I think that will be okay. Now, at least we've got cos and sines, which is what we had before. It doesn't look as easy to deal with. I sort of just hope that if you squared both, and I squared this out, expanding out brackets and stuff, I squared both, and then just decided to add them together in the hope that things would cancel, and they sort of did. Of course, when you add these together, sine squared plus cos squared is 1, so you just end up with a 1/4, which adds with there to make a half. So this is sort of okay, but this doesn't look like... I still don't really know what this is, and I kind of want to know what it looks like just because I've drawn all the other ones, so I just wanted to know. But the thing is here, we can look at this guy here, minus a half cos theta, and just say, well, that's right there. So this is v minus a half. So that there is v minus a half. So that makes this just v minus a half, because the whole thing is minus that, so replace it with yeah, sure. Half minus a half is 0. So this is looking more promising. And in fact, what I can do here to make it very much like part 1, thinking about circles, is I can just complete the square on this a little bit. Just very quickly complete the square, halve down 1 for a half, take away that thing squared, and then move it over. And now I think this is a circle centered at 0, a half, radius a half. So it therefore looks a bit like this. This is the point 0, a half, radius a half. And just like the very part 1, just for the final mark of this question, because we use the same sort of substitution, theta is pi is still going to be an issue. And so therefore, when theta is pi, we have u is 0, and v is, well, cos pi is minus 1, so that makes a plus, that makes v is 1. So it's going to be an issue at 0, 1, which is here, just like it was before. And that'll be the whole question done. Thank you for watching, and I'll see you next time.